a skateboard? Kind of? The answer is, wow, Mr. Sheldon, your skills at drawing a skateboard are phenomenal. That's the right answer, skateboard. How many of you have ridden a skateboard? So it's not really a penny board, but it's not also a longboard either. I have exaggerated the rear step portion of the skateboard on purpose to identify that part of the skateboard. Now, skateboards have evolved a lot since the 50s when they were all the rage at the beginning, and then they went away and then they came back again. But generally, a skateboard is something that most of you have some familiarity in riding or falling. What forces are acting on the skateboard before any foot is placed on it? Can you identify the forces on the skateboard? In your drawing of a skateboard, could you please draw a few arrows? I'm thinking you probably have 3 arrows. If you don't, you've done something wrong. And as I said, I don't want to spend a lot of time on this, but I'm thinking you have a normal force on the back wheels, normal force on the front wheels, weight. Did anybody indicate any other forces? Yes, ma'am? There could be some friction. The friction would be in the ball bearings themselves, because there's definitely friction acting at the point of contact here, but that friction keeps the wheel from sliding. So there might be a frictional force here or there. I don't disagree with that. When you ride a skateboard, are these two normal forces the same value? It's not too hard to imagine that they have to equal mg, right? Would you all agree with that statement? Otherwise, the skateboard would be accelerating downwards, bless you, or accelerating upwards. If it's just resting on the ground, that has to be true. Now, again, the question, do the two normal forces have to be the same? Now, if you place your foot and press down in the middle, you could probably distribute your weight between the two wheels. But most of you also know that you could press down here and that would kick up the front wheel while leaving the back wheel on the ground, correct? In fact, a smart student, and there are many in this room, would recognize that the force from your foot here could slowly increase until this normal force became 0. That would be the moment the front wheels leave the ground, when they are no longer touching the ground, right? The ground can only apply a normal force when it's touching it. The moment that normal force is 0, it's not touching anymore. Now, that suggests, though, that this normal force has had to get a lot bigger for the skateboard to still stay in place, which is what's happening. Skateboard is still on the ground. The front wheels are just no longer touching the ground. And we have an additional force on the system. The weight hasn't changed. I bet that normal force has gotten much bigger, while this normal force has disappeared entirely. Do you understand that that qualitative analysis is something I will expect you to be able to do? This became the pivot point. A torque was applied here. A torque that was greater than the torque applied here. And although the net force on the system was 0, net torque maybe not. These kinds of qualitative analysis is what I expect. I didn't have to teach you anything new. All of this is information you have, but we're applying it now. I want to apply this to the bridge question. The bridge question is a fairly traditional question. It's brought up in a number of different ways. This is not the only way the bridge question gets discussed. It's just one of many. The bridge question is a good statics example. A statics example is an example or something that exemplifies a static condition. Basically, we've studied statics before. Statics is any time the net force equals 0 and your system doesn't move. Basically saying your system doesn't move means the net force equals 0. So statics problems tend to be ones where things are staying still. By definition, your system could be traveling at constant velocity and still be described as a statics problem. But most statics problems are static in that they are staying still. Now, calling this a bridge is calling your attention to the idea that the road surface might meet the bridge, but then it cuts away. Thus, we need a bridge to span some section of ground. Does that make sense? Bridge problem. So we're expecting that on our bridge might be cars that are driving across the bridge. Now I want you to imagine a car traveling across the bridge and passing over these letters. At any one time, how many forces are acting on the bridge? Hold up the number of fingers that represent the number of forces acting on the bridge. Please. All right. I'll remind you that a force is applied by either something fundamental or something in contact. So I count 4 forces, 3 points of contact, and 1 fundamental. There's clearly going to be the weight of the bridge. There's going to be the weight of the car. There's going to be the normal force from the right pylon and the normal force from the left pylon. I believe we've exhausted all the forces that act in this system. Four forces. For the bridge to stay where it is, we know the net force has to equal 0. But as just described with the skateboard, that's not enough. It is possible something heavy enough could enter the roadway and cause the bridge to start to rotate. Right? If it showed up at A heavy enough, it might lift the bridge off the pylon over here. Just the same way that our skateboard pivoted. A true static condition has 2 conditions that must be met. The net force must be equal to 0, and the net torque must be equal to 0. So now, qualitative questions. As the car progresses across the bridge, can you pick out where the car could be where the forces from the pylons would be equal? Can you pick out where the car would be so that the force on pylon to the left is greatest, or where the force on the pylon to the right is greatest? Can you recognize that as the car goes from right to left, that the force from the 2 pylons is going to be changing? When the car is at B, do you realize that the pylon to the right is going to have to support more of the car's weight than the pylon to the left? C as well? When it's at F, though, clearly the pylon to the left is going to support more of the weight than the pylon to the right. Fair enough? All right. I want to make sure that you understand that this is a qualitative discussion right now, but we could do a very real quantitative discussion. Does everybody understand? Now, in fifth period, we did this problem, and the car is placed at C. In this class, we're going to do the problem with the car placed at A. That way you can compare what happens. Does everybody understand? Because I would like you to be able to see it all, but I don't want to do all 3 or 4 different possibilities. So for us to do this, I'm going to place the car at A. I'm going to put some specifics to where these things are, and then we're going to work the problem. We're going to use the same numbers as was used in fifth period, and they got to make these decisions, so I'm sorry. They said the mass of the bridge was 10,000 kilograms. They said the mass of the car was 1,000 kilograms. The bridge is 100 meters long. The bridge is 100 meters long. But this pylon is 20 meters from the end of the bridge, and this pylon is 20 meters from the end of the bridge. We're going to place the car 15 meters from the pylon. We will assume the bridge's weight is distributed at its center, that it has a center of gravity at its center. Okay? Is everybody ready? Now, this problem, it's not that it's hard, but like force, it sometimes takes some practice to understand all the principal parts of a problem like this. First, the net force part of these problems tends to be pretty easy. We know it equals 0, but there are only 4 forces, 2 act up and 2 act down. There's the 2 normal forces. They act upwards. They have to be balanced by the 2 forces that act downwards. The weight of the bridge which is 100,000 newtons, mg, plus the weight of the car, which is 10,000 newtons. The first thing I need to point out is that the reason we talk about torque is because sometimes talking about force isn't enough. With everything we've done so far this year, we've always been able to narrow down one of the forces using net force. This is the first time where that's not true. We have 2 unknowns and no other information to go on if all we have is force. That the 2 forces sum to equal the force of the bridge and the car. We knew that already. We just don't know how much each has to supply, and we know it changes as the car goes across the bridge. So now we have to figure out how to use torque to solve this. Now to do that part of the problem, I am going to go to something that's a little bit cleaner, to clean this up a little bit, to make it easier for us to look at. Some of the normal forces equal 110,000. So you have it in your notes, so you can easily flip back and forth. I'm going to make a nice clean interface. And I'm just going to apply the forces where they act on the object. This is what I would do. We can't use a free body diagram anymore. A free body diagram is great for forces, but for torques, we need to know where the forces act. You'll still be required to draw free body diagrams, but when you have to go for the torque, you'll need a torque diagram. A torque diagram identifies where the pivot is and the point of application of all the forces. Usually it can be narrowed down to a bar, but often we just draw the shape of the object. Now you should draw 4 arrows here, one for each of the forces. And this isn't hard, so I'm going to race you to it. There's an L, an R, 100,000, 10,000. Now, this next thing is important. You should write it all down, but only one of them applies to this. If a pivot isn't given, if there is no axle or axis, then 2 things apply. Either the object rotates about its center of gravity, or in the case of a statics problem, you can choose the pivot point. So, if there's no fixed axis, either the object rotates about its center of mass, or in the case of a statics problem, you can choose the pivot. The reason you can choose the pivot is the net torque is 0. It's not pivoting, so every place can be your pivot. Now, this part's incredibly important. Every place can be your pivot. You can choose anywhere you want to put the pivot point. It makes no difference. The problem will still solve to the same answer. But this part's important. This is the problem-solving part. This is the stuff that you guys screw up because you don't really pay attention. You just act like it because you don't know how. But this is a lecture class, so I'm telling you how. If you want to make the problem solvable, place the pivot someplace that cancels out an unknown. If you want to make your problem solvable, cancel an unknown. Put your pivot someplace where a torque arm length will be 0. There are 2 unknowns here. I don't care which one is our pivot, the left one or the right one. It will make no difference. The problem is the same. So where do you want to place the pivot, left or right? So our pivot is at the right. Excellent, because 5th period made it the left. Now, once you choose a pivot, you should also choose a direction that you call positive. This direction is about rotation, so we can determine whether our torques are positive or negative. Your book is forcing you to use this way as positive. Your book is doing that. Just like they always made up positive, they're choosing out of the page as positive, or counterclockwise as positive. That's your book. You know, I don't care what direction is positive, right? But if you're consistent, you'll be happier. Now, here's where things get a little bit different than force. With forces, we broke things up into the x direction and the y direction. We don't have to do that for torque, because our torques are all going to act along one axle. So they're basically one-dimensional. But we do have to deal with the fact that it's a torque. And torque is R times F times the sine of the angle, and they're all plus or minus. So torque's a little more complicated. We have 3 torques acting in this problem. Only 3 because we canceled out one of them on purpose. Now, we could have put the pivot someplace to make there be 4, but you understand, the better you do this, the easier the problem will be. 3 torques. There's one for the left pylon, There's one for the bridge and one for the car. And for each one of these, we have to decide what the torque arm length is, whether it's positive or negative, and what the force is, and finally the angle. It's a lot. So, which one do you want to do first? Let's do the car first. Not a problem. In order to do this, it's probably a good idea for you to figure out all the distances from the pivot to where the forces are. I've identified the distances we need. I'll give you 30 seconds to figure out what those three numbers are, and then I'm calling you out. I'll be calling out 3 people. You have 15 seconds left. And since it's nobody's birthday today, I won't feel bad if I call out a birthday kid. Now, you've actually had your 30 seconds. Right now, you're on borrowed time. Hogsmeade, give me one of them.
The distance to the left pylon is 60 meters.
Distance to the left pylon, 60 meters. Good. I would agree with that. Because if it's 100 meters total, 20 meters in on every side, that's 60 minus 20. 100 minus 20 minus 20 is 60. Good job. So now, it's Hogsmeade again. Nope. Halo array, give me another.
The car to the right one is 15.
Excellent, 15 meters. And Bikini Bottom. Well, that sucks. There's only one of you there. You don't get to rely on anybody else.
65 meters for the center to the right.
Nope.
Hold up, never mind. Oh, I meant 30 meters.
All right, I'll give you that. I'll give you another try. There's only one of you there. Good job. Those are all our torque arm lengths. Is the car causing a positive or a negative torque? Negative. Is the bridge weight causing a positive or a negative torque? Is this pylon causing a positive or a negative torque? All of that's true. Figure it out tonight. I'm going to continue and talk to the iPod as you guys leave, and then I will make sure this gets posted this evening. The force is unknown, sine of 90. The next one, acting at 30, force is 100,000 newtons. Again, sine of 90. And the last one, 15, 10,000 newtons, and sine of 90. For the net force to be 0, these have to sum to be 0. Bye, have a good day, guys. Bye-bye, guys, have a nice day. Now, our job is to figure out what this normal force is, the normal force from the left pylon. We're going to create a sentence with this. We're going to add all these 3 up and set them equal to 0. So this will be negative 60 times n plus 3 million minus 150,000 has to equal 0. So that is 3,150,000. All right, so I'll move the other one to the other side, and I'll get 60 NL. So NL will be 3150000 divided by 60, or which means 52,000 newtons. Now remembering, then the normal force on the right has to be 110,000 minus 52 500, which is 57,500 newtons. We knew already that the normal force on the right was going to be greater than the normal force on the left. Now we know by how much. Make sure you compare this to what we did in fifth period.